Alright, so let's start with part A. So, a box, a book with mass 34 kilograms just on the floor of a campus bookstore. The floor is structurally waxed and has natural friction. A bookstore worker applies a constant horizontal force with magnitude 25 newtons. The box is the magnitude of the acceleration of the box. As the magnitude acceleration of the box. So, let's go ahead and write A. Cool. So for part A, we're given a mass of 34 kilograms and a horizontal applied force of 25 newtons. And the floor has been freshly waxed, so it's assumed frictionless. So first I must isolate a little box and just draw a free body diagram. So I'll just go ahead and use this box to represent it. And from the center of the square, I'll just go ahead and draw a horizontal arrow pointing to the right and label it F for force. And I draw it to the right because that is the direction of the applied force and therefore the direction of the acceleration. I'll just go ahead and then draw a vertical arrow aiming upward from the center and label it normal for normal force, right? And then we'll just have one pointing straight downward from the center labeled weight equals mass times gravity. And so this friction is negligible. I do not have to draw any friction force. And of course, I'll just go ahead and choose positive x to be to the right. And so then we can just go ahead and write the sum of forces in the direction of x is equal to mass times acceleration. Since the only horizontal force is F, just go ahead and write that as F is equal to mass times acceleration. But we're solving for acceleration, so that's A, or A for acceleration, is equal to force divided by mass, and then we just go ahead and apply and plug in those numbers. So 25 newtons divided by mass, so 34 kg meters per second squared. Go ahead and take a calculator. 25 divided by 34, that's A, or acceleration, is equal to 0.735 meters per second squared. But we're going to go ahead and round that up to 0.74 meters per second squared. And now we can just go ahead and move on to part B. Block of cheese of 1.8 kilograms sits on a freshly waxed, essentially frictionless table. You apply a constant horizontal force of 0.50 newtons to the cheese and select 3 external forces that act on the cheese. Okay. So for part B, it's asking us to isolate or identify the external forces acting on the cheese. So I'll just go ahead and isolate the cheese as a little block, and I'll just go ahead and make that a little square, in order to represent the cheese. So from the center of the square or cheese, I'll just go ahead and draw a horizontal arrow pointing to the right and label it F. For the applied force, I draw it to the right because the problem states the cheese accelerates horizontally, and the applied force must point in the same direction as that of the acceleration. I'll then go ahead and draw a vertical arrow upward from the center, label that N for normal force, and then I can just go ahead and draw another one pointing downward from the center and labeled it weight is equal to mass times gravity. and that'll be for the weight. And because the table is essentially frictionless, I do not have to draw any friction force, and therefore there are only 3 external forces acting on the cheese. So that would be normal force, its own mass, or just weight, and of course the applied force. So that's normal force, that's its weight, and applied force. We can just now go ahead and move on to part C. Determine the direction of these forces. Okay. So, all right. Part C asks for the directions of these forces from the free body diagram. So, of course, the normal force is pointed upward, right? Cool. And then the applied force. The applied force is horizontal. Along A, or acceleration, and then of course W, or weight equals mass times gravity, is downward. Nice. And so those would be the answers. Now we can just go ahead and can you see it? I think you can see it. Yeah. Yeah, you can see it. Move on to part D. What is the magnitude of the acceleration of the cheese? Okay. So for part D, it's asking us for the acceleration of the cheese itself. So we know the mass is 1.8 kilograms, and the applied force is 0.50 newtons. So I'll just go ahead and redraw the free body diagram. I'll go ahead and draw the square, and from the center I draw a horizontal arrow to the right, labeled F. For the applied force, I draw to the right because that is a direction of the motion and acceleration. I'll go ahead and then draw the normal force. Label that N for normal force, downward arrow. Label that W is equal to M times G, or weight is equal to mass times gravity. And there's no friction, so we do not have to draw an arrow for that. So we can just go ahead and move on to the sum of all forces along X are equal to mass times gravity. And since the friction is negligible, this now becomes F, or force, equals mass times gravity. But we're solving for the acceleration. So let's go ahead, manipulate that into A for acceleration is equal to force divided by mass. We'll go ahead and plug in those numbers. So 0.50 newtons divided by mass, which is 1.8 kilograms, meters per second squared. And go ahead and plug those into a calculator. 0.50 divided by 1.8. We have, that's wrong. 0.2777, and there is a trail of numbers, but we will go ahead and round up today and that'll give us the answer of acceleration is equal to 0.277 meters per second. Oh, sorry, I did not round. 0.278 meters per second squared. That is our answer for part D. We'll go ahead and move on to part E. Cool. Alright, so in the game of hockey, you use a hockey stick to hit a puck of mass of 0.16 kilograms that slides on essentially frictionless ice during the hit. You exert a constant horizontal force on the puck that gives it an acceleration of 75 meters per second squared for a fraction of a second during the hit. What is the magnitude of the horizontal force that you exert on the puck? Cool. So for part E, the puck has a mass of 0.16 or 0.16 kilograms and an acceleration of 75 meters per second squared. And the ice is once again assumed frictionless. So I'll just go ahead and I'll draw a free body diagram. I'll make a little circle for the puck. And from the center, I'll draw a horizontal arrow to the right, labeled F, for the applied force from the stick. And since that is the direction of the acceleration, I'll draw a normal force arrow upward, label it N. And then an arrow pointing downward and label that W is equal to mass times gravity, or weight is equal to mass times gravity. And we don't have to draw anything to the left because there is no friction. So once again, choosing X to the right hand side to be positive, we can now go ahead and move on to the equation. Just go ahead and write the sum of forces along X is equal to mass times acceleration. But we'll go ahead and just write that as force is equal to mass times acceleration. And then we can just go ahead and plug those numbers in. So 0.16 kilograms times acceleration. Yeah, F is equal to mass times acceleration. I apologize if I said something different previously. I've had to film this video quite a few times, so I'm losing my mind a bit here. Nonetheless, I apologize. Let's get back to the homework at hand. So we're just going to go ahead and replace M for mass as 0.16 kilograms multiplied by acceleration, which is 75 meters per second squared. And of course, we are solving for force, so that would be measured in newtons. So force is equal to, let's go ahead and plug those numbers into a calculator. 0.16 times 75. That'll give us a very nice round number of force is equal to 12 newtons. Cool. And now that's part E. And before moving on to part F, well, actually, I think I still have some space. Well, no, I'm gonna flip the page. And set it up once again so you can see me properly. Cool. Now, part S says, how does the magnitude of the normal force N due to the ice compared to the weight W of the puck? Okay. So part F compares the normal force and the weight from the previous free body diagram, and there is no vertical acceleration, only horizontal within this particular problem. So we can just go ahead and write sum of forces along y equals mass times acceleration along the y-axis, and that simply equals 0. So normal forces minus weight equals 0. There's nothing to calculate here because they're in perfect equilibrium, so they just cancel out and they're equal to each other. So normal force is equal to weight. Nice. Now go ahead and move on to part G. Okay, so a plate of cafeteria food is on a horizontal table. You push it away from you with a constant horizontal force of 14 newtons. The plate has a mass of 0.800 kilograms, and during the push, it has an acceleration of 12 meters per second squared in the direction you are pushing it. What is the magnitude of the net external force on the plate during the push? Okay. So, the plate has a mass of 0.800 kilograms and acceleration of 12 meters or 12.0 meters per second squared in the direction of the push. I'll go ahead and draw a free body diagram. I draw the plate as a square. From the center, I can draw a horizontal arrow to the right, labeled F. For the push, because that is the direction of the acceleration, I'll go ahead and now draw a horizontal arrow to the left. A little bit shorter than the one on the right hand side, and label that lowercase f for friction. And since friction always opposes motion, I draw it to the left hand side. Now I'll just go ahead and draw the normal force, which is perpendicular, and so that in this instance that is directly upward. Label it N, and then we'll draw another one straight downward for its own weight, which is weight or mass, gravity. Weight equals, right, to mass times gravity. Right, so the magnitude of the net external force is given to us by Newton's second law. So we'll just go ahead and write that as F net equals to mass times acceleration. F net for net force is equal to mass, which is 0.800 kilograms multiplied by the acceleration, which is which is 12.0 meters per second squared. Nice. Of course, we're solving for net force. So that would be in newtons. After doing some simple calculations on the calculator, we get a nice round number of net force, or F net, is equal to 9.6 newtons. Nice. And we can just go ahead now and move on to part H. What are the magnitude and direction of the friction force that the table exerts on the plate during the push? Okay. Can you see? Okay. So part H asks for the friction. So I'll just go ahead and define positive x to be the direction of the acceleration, which is to the right. And from the free body diagram, the horizontal forces are F, push, right? The applied force to the right, and friction to the left. So if we just go ahead and apply Newton's second law, we can just go ahead and write the sum of forces along x, or in the direction of x, equals mass times acceleration. And so we want to find out what that friction, right? What that friction number is in newtons. So in order to do that, we have to go ahead and write down F push for the applied force plus friction, because we want to get the net forces here, and that'll give us our net force. But let's go ahead and substitute this really quick. That'll be 14.0 plus F friction is equal to 9.6 newtons. But we don't yet know what this number for friction is quite yet. So we just have to go ahead and manipulate the equation to this. F equals 9.6 minus 14.0. And if we go ahead and plug that into a calculator, 9.6 minus 14.0, we'll go ahead and get our final answer. And that is that the opposing value, or the friction, is equal to negative 4.4 newtons in the opposite direction.